Differential equations play a crucial role in running and analyzing numerous real-world systems. Be it some of the complex electrical circuits or hydraulic outputs, differential equations help in analyzing and improving data in countless such scenarios. Let's try to understand how we can form the differential equation with the most comfortable illustrations. Formation of differential equations. You've probably dealt with a whole lot of equations in your algebra classes. Some equations are really simple ones like x plus 3 is equal to 1, which can be solved in a single step. You also might have come across some second degree equations like x squared minus 2x plus 1 is equal to 0. These also can be solved in a couple of steps. In all these equations, you can see that the solutions are actually numbers. Do all equations have numbers as solutions? Let's peep into the type of equations whose solutions are not just real numbers but functions. These are called differential equations. An equation involving derivatives or derivatives of the dependent variable with respect to an independent variable or variables is called a differential equation. We've already seen differential equations have solutions that are functions. If we plot these solution functions on a coordinate plane, it could be a single curve or a family of curves. These family of curves are basically the geometrical representations of the solutions of the differential equation we started with. Now, what if we have such a function to start with and we need to form the differential equation whose solution is that function? Let's consider one of the simplest family of curves, the straight lines that pass through the origin. The equation representing the straight lines passing through origin is y is equal to mx, where m is the slope of the line. For various values of m, we get different lines. How can we convert this to a differential equation? Well, we've already seen that differential equations contain derivatives. So the first step is to differentiate the equation with respect to the independent variable x. Another important thing to be noted is that a differential equation should not contain arbitrary constants. Here in the equation we started with, we have an arbitrary constant m. So to eliminate the constant, substitute dy by dx for the constant in the original equation. That is, y is equal to dy by dx times x, or y minus x times dy by dx is equal to 0. Thus, we have a differential equation corresponding to the family of straight lines passing through the origin, free of arbitrary constants. Next, let's take a bit advanced one. Consider the family of all straight lines. These can be represented by the equation y is equal to mx plus c, where c is the y-intercept of the line. There are two arbitrary constants, m and c, and we need to eliminate them. So how can we do that? Upon differentiating the equation with respect to x, we get dy by dx is equal to m plus 0, or dy by dx is equal to m. Are we done? No. Even if we substitute the value of m in the original equation, we'll be left with one more arbitrary constant, c. We do need three equations to eliminate two arbitrary constants. So, differentiate again. Then we have d2y by dx squared equal to 0. Thus, we have a second order differential equation that we got by twice differentiating the equation of the family of straight lines. Or, in other words, the solution of the differential equation d2y by dx squared equal to 0 is the family of straight lines. Did you notice that when we started with an equation that has only one arbitrary constant, we got the corresponding differential equation by just differentiating once? Or the corresponding differential equation is of first order. Next, we started with an equation that has two arbitrary constants. we had to differentiate it twice to get a second order differential equation. Now, can you guess the order of the differential equation if the given equation has 3 arbitrary constants? Yes, it will be a third order differential equation. Let's generalize this result. Start with a function in independent variable x and dependent variable y that has n arbitrary constants a1, a2 and so on till an. How can we form the corresponding differential equation then? The first step is to differentiate with respect to the independent variable. Since there are n arbitrary constants in the equation we started with, differentiate n times so that we have n plus 1 equations to eliminate those n constants. Now we have n plus 1 equations using which we can eliminate the n arbitrary constants in the equation we started with. That is, if we start with a function with n arbitrary constants, the corresponding differential equation will be of nth order. Now that you've understood the concept of forming a differential equation from the equation of a family of curves, let's try this with an example. Form the differential equation corresponding to the family of curves represented by the equation y is equal to a cos 5x plus b sin 5x. Here you can see that there are 2 arbitrary constants a and b. As per the rule, since there are 2 arbitrary constants in the equation of the family of curves, the corresponding differential equation will be of second order. First, differentiate the given equation y is equal to a cos 5x plus b sin 5x. Since a is a constant, the derivative of a cos 5x is a times minus sin 5x times the derivative of 5x, that is equal to minus 5a sin 5x. Similarly, the derivative of b sin 5x is b times cos 5x times the derivative of 5x, that is equal to 5b cos 5x. So dy by dx or y dash is equal to minus 5a sin 5x plus 5b cos 5x. It is not possible to eliminate arbitrary constants using these 2 equations. So differentiate again to get the third equation. The left-hand side of the equation becomes the derivative of the first order derivative, that is d2y by dx squared or y double dash. Now let's differentiate the right-hand side. Using the same rules of differentiation, we can find the derivative of minus 5a sin 5x plus 5b cos 5x as minus 5a times cos 5x times 5 plus 5b times minus sin 5x times 5. This can be simplified to minus 25a cos 5x minus 25b sin 5x. Taking minus 25 common from both the terms, we have minus 25 times brackets a cos 5x plus b sin 5x. Looking at the expression within the brackets, we can see that it is precisely equal to y from the equation that we started with. That is, the whole expression becomes minus 25y. Thus, we have a differential equation we got by differentiating the given equation twice, and it is free of arbitrary constants. So the required differential equation is d2y by dx squared is equal to minus 25y, or d2y by dx squared plus 25y is equal to 0. Thus, we have formed the differential equation corresponding to a family of curves with the given equation. Let's summarize what we've learned in this video. An equation involving derivatives of the dependent variable with respect to the independent variable is called a differential equation. Differential equations have functions as solutions. To form a differential equation from an equation of a family of curves, first differentiate with respect to the independent variable. Continue the differentiation n times to get n plus 1 equations. Now eliminate the constants a1, a2 up to an using these n plus 1 equations to obtain the differential equation free of arbitrary constants. We've also learnt that the order of the differential equation is equal to the number of independent arbitrary constants in the given function and is derived from these constants itself. You must be wondering how something this important is so easy to formulate and grasp. But wait, how do we obtain the family of curves if the differential equation is known? Stay tuned to know more.
Keep imbibing. We believe in you.